This is problem 1 on practice exam 1 of module 7 in the book Problem Solving Guide for Mechanics and Thermodynamics. We have a 12-foot long plank at rest on 2 sawhorses. Plank has a mass of 8 kilograms. Distance between the centers of the support points of the sawhorses is 8 feet. 3 feet of the plank is over the right sawhorse. 1 foot is over the left sawhorse. What's the normal force on the plank from each sawhorse? Part B, stick an 80 kilogram painter on the plank 3 feet from one end. What's the normal forces now? We need a good diagram. There we go. Let's add in the distances. We have a 12-foot plank. The sawhorse on the left is 3 feet from the end. The sawhorse on the right is 1 foot from the end. Now we'll add in the forces on the plank. We have the gravitational force at the center. We have the normal force from the right sawhorse and the normal force from the left sawhorse. Those are the forces. These two forces must add to that force. We know that the combined forces from the 2 sawhorses must sum to 80 newtons, the weight of the plank. If we get one of the forces, we can get the other by subtracting one of them from 80. So let's take torques about this point right here. We could do any point. I'm choosing this one. That's my axis of rotation. So we need the distances from this point to the other forces. Let's put them in. This point is 3 feet from the center of gravity and 8 feet from the other sawhorse. The clockwise torque is from the gravitational force. The gravitational force is already at a right angle to the distance and it's 3 feet away. The torque is the force times the distance, which is mg times 3 feet. The clockwise torque from the right sawhorse, it's 8 feet away and the force is F normal right. There we go. These torques have to balance because the board is static. It's not rotating. So we set them equal. And we stick in 80 newtons for mg, the weight of the board. We can solve for the normal force from the right sawhorse, and that is 30 newtons. And if that's 30, that has to be 50. They both have to sum to 80. For part B, we have to add a painter. There he is, 3 feet away from the end of the board, as it says in the problem. He has a mass of 80 kilograms, so I'm not going to be able to draw this to scale. It's 10 times bigger than this vector. He's pushing down on the board with a force of 800 newtons because he has a mass of 80 kilograms. Yes, the plank is pushing up on the painter, but we don't care about the forces on the painter. We are isolating the board, saying, is the board rotating? What are the forces on the board? So we're only interested in the force on the plank, so let's add this force to the diagram. It should be much bigger than that. Certainly, with the painter close to this sawhorse, this normal force is going to increase. It's going to be much bigger than this one. So let's just do the best we can there and draw a bigger vector like that. Now I'm going to take torques about the right sawhorse, just to demonstrate it can be done about any point. Painter is a horizontal distance of 2 feet from this point because he's 3 feet from the end and the sawhorse is 1 foot from the end, so that's 2 feet. About this point, we need some distances here. What's the distance from gravity? Let me see, gravity's in the middle. It's a 12-foot board, that's 6 feet, that's 1 feet, so gravity has to be 5 feet away from the right sawhorse. Now we can take some torques. This diagram is a little crowded, but it's neat and it makes things a lot easier. We have the distances and the forces. And we have a well-labeled point of rotation. It's like we pinned the board down right there. It's pinned down right here. We want to know which way are the forces spinning it. This normal force is not exerting any torque about this point. The only clockwise torque is from this guy. Tick, 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 clockwise. These two forces are counterclockwise about this point. They go backwards. That one's clockwise. So this guy is 8 foot away, the other sawhorse, and the magnitude of the force is F normal from the left. So that's the clockwise torque. That's the only one. The counterclockwise torques our gravity times 5 feet and the painter times 2 feet. Yep. We know what these forces are. This one's 800 newtons, this one's 80 newtons. So we set the torques equal. Clockwise torques equals the counterclockwise torques. And we know those forces. The force from the painter is 800 newtons. Force of gravity on the board is 80 newtons. And we get 2,000 newtons feet is 8 feet times the normal force on the left sawhorse. We can solve for F and L by dividing by 8 feet. And we get 250 newtons. This is 250. The total weight is 880. The painter's 800, gravity's 80. The total downward force is 880. If this one is 250, this one has to be 630. 880 minus 250. So this one's a lot bigger than that one. Let's check this. And let's take torques about a different point because we're practicing. Instead of taking torques about this point, I'm going to go all the way over here. Take torques about this end. Just for fun. So now we have all the distances almost. Well, this guy, we're not going to label this one. The whole board's 12 feet. That's 1 feet. So this force is 11 feet away from this point. And we're going to add these two distances. That's 6 feet. Gravity's 6 feet from the end because it's in the middle of a 12-foot board. And the painter is 3 feet from that end, which is 9 feet from the left end. Okay, I think we're ready to go. The clockwise torques about this point. Tick, tick, tick. Gravity, that's down. Gravity is 6 feet away times F gravity. Painter's 9 feet away. F painter, sticking in the numbers. 8 times 6 is 480. 800 times 9 is 7,200. We add those up and we get 7680 newtons feet for the clockwise torque. If we did it right, we better get 7680 newtons feet for the counterclockwise torque. All right, the counterclockwise torques about this point are from the two normal forces. Those are anti-clockwise. We have the normal force from the left sawhorse is 3 feet away, and the normal force from the other sawhorse, the right sawhorse, is 11 feet away from this point. And we calculated these values. We hope we're right. This one's 250, this one's 630. So we can plug them in. 250 is 3 feet away, 630 newtons is 11 feet away. Multiply this out, we get 750, 6930, and we add them up. 30 plus 50 is 80, 69 plus 7 is 76. Oh my God, it's 7680, which is the same as the clockwise torques. Hallelujah. Are you surprised? I don't know, I'm kind of surprised. That was a lot of work, and we got the right answer. Congrats.